Ladies and gentlemen, if you're after something that could further push the envelope of comminution and flotation, I hope you will find my presentation useful. To enable energy-efficient comminution and flotation, we are doing online monitoring of hydrocyclone overflow. As can be seen in this diagram, our project belongs to comminution. As a classification device, a hydrocyclone plays an important role in linking comminution to flotation because flotation takes its feed from hydrocyclone overflow. So, what exactly are we monitoring at hydrocyclone overflow? It is particle size. Then why are we interested in particle size? Why does particle size matter? It is because knowledge of particle size at hydrocyclone overflow not only tells the quality of mill discharge, hydrocyclone performance, and flotation feed, but also greatly helps enabling energy-efficient comminution and flotation. Now let's take a look at the figure on the left-hand side, which shows copper recovery against particle size under different operation settings. We can see a common pattern among all curves. That is, for maximum recovery, the particle sizes should be neither too small nor too large. This is a useful fact from the perspective of comminution. Looking at the figure on the right-hand side, we can see huge energy consumption if particles are ground to very fine grains. Now recall that maximum flotation recovery requires an optimal particle size, which does not necessarily to be very fine. This means we can reduce the grinding task by only grinding to the optimal particle size. And in this case, we will be looking at some points towards the right side of the curves, which are associated with much less energy consumption. So, how do we tell whether we are grinding to the right particle size? We need particle size information. Traditionally, particle size analysis is done offline, which can introduce hours of delay. To allow optimal control of the grinding circuit, real-time feedback of particle size information is necessary. Now, suppose you've got something that could do online measurement of particle size at a central overflow line where the overflow of individual hydrocyclones merge together. One day, it reports a sudden increase of coarse particles. Then the questions are, where does the problem come from? Is it from the grinding device or from hydrocyclones? If from hydrocyclones, then which unit is malfunctioning? Now, it turns out every hydrocyclone unit should also be monitored individually. Then the next question is, how much will this cost? Well, that depends on the cost of sensors and the way they are installed and maintained. Indeed, there are a number of choices available, which, however, are also costly and bespoke. As can be seen in the figure, hydrocyclones are normally arranged in a group, and there could be dozens of or even hundreds of hydrocyclone units at a processing plant. This means the total cost could go drastically high if every hydrocyclone unit is to be equipped with a monitoring device. Then we might be facing a dilemma of whether to remain the traditional operation or to invest on real-time monitoring. So, are there any other feasible solutions? The answer is yes. We have a solution for you. We have developed a force measurement unit with a probe penetrating into the overflow pipe to measure the force from the incoming slurry. One of the interesting findings is the measured forces can be categorized into two types. One is the particle probe impact dominated by coarse particles. The other is the flow-induced drag dominated by fine particles. The coarse particles generally have sizes similar to very fine table salt or even finer, and fine particles are normally as fine as powder. We have found both the particle probe impact and flow-induced drag have their exclusive signature frequencies that are associated with the corresponding size distribution. Using the force measurement, we can also determine the mass flow rate without the need for a separate flow meter. By synthesizing these two types of information together, we can obtain the size passing fraction of a target's particle size. For example, if you are interested in monitoring P80 of 75 microns, then our device will give you a reading in percentage, showing the fraction of particles that are smaller than 75 microns. To study particle probe impact mechanisms, we have done dry tests in the air using sand particles in free fall from a certain height. We have also put the probe in slurry flow to investigate flow-induced drag and the combined effects with particle probe impact events. In these tests, we have considered more complicated scenarios involving the presence of air bubbles, turbulence, different solid concentrations, etc. Now, the most exciting part. Let's see how our sensor performs. The red curve shows the cumulative percent passing of sand particles we use in experiments, which is done offline using laser diffraction methods with a residual error of less than 1%, so we use it as a benchmark for comparison. Our sensor could estimate the size passing fraction of specified target sizes. So when we look at the size on the horizontal axis, it gives the corresponding percentage reading, shown by the scattered dots colored according to different solid concentrations. The smaller distance between the dots and the red curve, the better estimation. As can be seen from the results, there is no apparent difference in estimation of size passing fraction under different solid concentrations. This shows good robustness of our sensor, which is not affected by variation in solid concentration. We can also see that the estimation error tends to become relatively larger for particles of fine sizes. This needs to be improved, and we are working on this at the moment. The possible cause of error could be with the identification of particle probe impact events, which can be affected by several factors including sensor noises and other vibration sources. So, we need more information. What if we measure vibration signals via accelerometers at different locations? One could be on the pipe that could tell the structural vibrations, and the other can be on the probe that could help verify particle probe impact events. Accelerometers couldn't be more common in our everyday life, which is versatile and low cost and can be seen almost everywhere, such as cars, smartphones, Fitbit watches, etc. It helps us identify and verify true particle probe impact signals, yet with only a little addition in cost. We are optimistic that the accelerometer integration will eventually improve the model accuracy and allow detection of particles above 50 microns. Our new sensor will deliver a number of benefits. First of all, it is cost-effective. The total cost, including initial installation and ongoing maintenance, will be only a tiny fraction of the other existing technologies. Secondly, it is a two-in-one sensor that not only estimates size passing fractions for target particle size, but also measures the real-time mass flow rate. Thirdly, it will be a perfect choice as part of a closed-loop control system that will automate the grinding task and hydrocyclone of operation to enable energy-efficient comminution. Last but not least, the operation is as simple as pushing one button for on and off and reading just two numbers, size passing fraction and the mass flow rate. The installation is easy as well, and the probe will only need to be replaced whenever the hydrocyclone unit is due for maintenance. So the downtime can be kept to minimum. This is not the end. What are we going to do next? Currently, we have found that the probe resonance is particle size dependent. As can be seen from the figure, the probe of different resonant frequencies is sensitive to particles of different size classes, where the torque amplitudes measured for different particle size classes have peaks at different probe resonant frequencies. Specifically, fine particle can be better identified with a high resonant frequency, while coarse particles can be better captured at low resonant frequencies. That means, to measure particles of a wide size range, the optimal stiffness of the probe should differ. So, what if the probe stiffness can be adjusted in real time? In this case, the probe will be able to sweep its resonant frequency across a wide range of interest and literally scan a wide range of particle size distribution. This will be an interesting and promising work, which, however, is out of the scope of a current project. We are very keen on working on this in the future to unleash the full potential of our new sensor. In the end, I would like to acknowledge the support from the state government of South Australia through the PRIF Mining Consortium and the tremendous helps from my supervisor, our end user partner, and translation partners. That's all my presentation. Thank you very much for your attention.